Okay, good day. Welcome back again to our calculus class. So we will continue discussing about limit. A general limit exists on function of x when x is equal to c. If the limit and if the left and the right hand limits are both equal. Now, we have limit of fx is equal to L as x approaches c. So in other words, function of x approaches L as x approaches c. So in this example, we have function of x 4x minus 5 if x is less than or equal to 2, and 3x minus 5 if x is greater than 2. So if we try to construct a table using x values to get the function of x, we have from the left 1.9, 1.99, and 1.999. So as x gets closer to 2, so we have the corresponding values. 1.9, function of x is 2.6. 1.99, the y is 2.96. 1.999, 2.996. On the right, from the right, we have 2.1, 2.01, 2.001 as x approaches 2 from the right. So we have the corresponding values. 2.1, 1.3. If 2.01, we have 1.03. And 2.001, we have 1.003. Now, if we are going to graph the function as function of x approaches 3 as x gets closer to 2. So can you see on the graph, as x gets closer to 2, fx is 3 from the left. Now consider this from the right. From the right, fx approaches 1 as x gets closer to 2. Okay? Therefore, limit of the function x does not exist as x approaches 2. Okay? So by looking at the graph itself, we can determine if the limit exists or not. So in this example, from the left, we reach 3. From the right, we reach 1. They do not meet on the same point. That is why the limit does not exist. Another example. Function of x as x approaches 0, given function of x is 1 over x squared. Now again, in this table here are the values of x with corresponding fx. From the left, we have negative 0.1, negative 0.01, and negative 0.001. And as you can see the values, we have 100, 10,000, and 1 million. Okay? The other side, from the right, we have negative 1. We have 0.1, 0.01, and 0.001. As you can see the values, we have 100, 10,000, and 1 million. But if we are going to graph the function, this is now the graph. The graph, as x approaches 0, the corresponding values of x, f of x, grow arbitrarily large. Okay? So this graph will continue as x gets closer and closer to 0. So the y-axis here is the asymptote of the graph. The graph will not touch the y-axis, but the graph will continue and continue and continue as x gets closer to 0. So this is a continuous graph. Therefore, limit of 1 over x squared as x approaches 0 does not exist. There is no limit, okay, as x approaches 0. Now, consider g of x is equal to x cubed plus 4x minus 5 over x minus 1. Now, in this case, as x approaches 1, we have a little problem here. As x approaches to 1, the denominator will be 0, and any fraction with a 0 denominator is undefined. Okay? But again, we will try it using values. As x is approaching 1 from the left, okay, ang may negative dire, as x approaching 1 from the left, we have 0.9, 0.99, 0.999. So, as x gets closer and closer to 1. And the other side, from the right, x is approaching 1 from the right. That's why the positive sign. We have 1.1, 1.01, and 1.001. Let us try to examine the values. We have 6.71, 6.9701, 6.997. From the right, okay, 7.31, 7.0301, 7.003. So, it means it will meet at 7. So, the limit of the g of x as x approaching 1 from the left and as x is approaching 1 from the right is 7. Therefore, in this example, limit exists. If a function approaches the same value from both directions, then the value is the limit of the function at that point. Therefore, the limit of g of x, x cubed plus 4x minus 5 over x minus 1, as x gets closer to 1 from the right and as x gets closer to 1 from the left is 7. Okay? Now, how about this? H of x is x squared minus x minus 2 over absolute value of x plus 1. And this time, we will find the limit of h of x as x approaches negative 1. So, let us try from the left and from the right. From the left, we have negative 1.1, negative 1.01, negative 1.001. Now, from the right, we have negative 0.9, negative 0.99, and negative 0.999. So, as x gets closer to negative 1. So, we have 3.1, 3.01, 3.001. The other side is negative 2.9, negative 2.99, negative 2.9999. In short, the limit of each x, as x is approaching negative 1 from the right, we have negative 3, while the limit of each x as x approaches negative 1 from the left is positive 3. If the left hand limit and the right hand limit are not equal, the general limit does not exist. Again, if the left hand limit and the right hand limit are not equal, then the general limit of that function does not exist. So, our answer here is D and E, or limit does not exist. Another example. Let us consider g of x is equal to x squared minus 4 over x minus 3. And we will find the limit of g of x as x approaches 3. Now, from the left and from the right. So, we have the values here of x, 2.9, 2.99, 2.999. Okay, as x is approaching 3 from the left. Now, from the right, as x approaching 3 from the right, we have 3.1, 3.01, and 3.001. So we have the values here, negative 44.1, negative 494, negative 4994. The other side is 56.1, 506.1, 5006. So in this case, limit do not or does not exist, or NL. If either the left hand limit, right hand limit, or both do not exist, then the general limit will not exist. Okay? Now, if you try to observe the values of g of x as x gets closer and closer to 3 from the left, it grows larger and larger and larger. While the other side also from the right, the values of g of x grows larger and larger and larger. So we can say that both left hand or right hand limit does not exist here in this function g of x, x squared minus 4 over x squared, over x minus 3. Now, our answer is D and E, or limit does not exist. Take note of this. A limit is the intended height of a function. So when we say limit, the maximum height of the function. Example, as x gets closer to 4, then the limit is there. The limit will exist only when the left and the right hand limits are equal. Then number 3, a limit can exist if there is a hole in the graph. A limit will not exist if there is a break in the graph. So, in short, if the graph meet from the left and from the right, then the limit exists. Okay? Now, we're going to evaluate limits graphically. As you observe, we can determine limits using graph. Look at this graph. This is a graph of a parabola x squared plus 2x minus 2. Now, what do you think is the limit of this parabola? As x approaches 2. So, as x approaches 2, the limit is 6. Look at the graph. This is 2, right? As x approaches 2, then the f of x is 6. This point here is 2, 6. That is why limit of the function x squared plus 2x minus 2 as x approaches 2 is 6. Okay. Now, number 2. In this example, x squared plus 2x minus 2, in which x is not equal to 2. So, when we say x is not equal to 2, okay, we have a hole here. Okay. So, a parabola with a hole in it. So, ini siya supposedly is a hole. Okay, may buho ni siya. Okay. Now, as x is approaching 2, then the limit is 6. Okay. Once again, the existence of a limit at a given point is independent of whether the function is defined at that point. So if I will say a parabola with a hole in it, that is x is not equal to 2. Okay. How about this? Function of x, x squared plus 4x plus 3 over x plus 1. This is a rational function and defined at x is negative 1 because x is, when x is negative 1, the denominator goes to 0, right? If x is negative 1, so negative 1 plus 1, that will be 0. However, x is equal to negative 1 is not a vertical asymptote. Let us see. If we are going to factor the numerator, we will get x plus 3 and x plus 1, right? Over x plus 1, so we can cancel out x plus 1 and x plus 1 here. So what is left is fx is equal to x plus 3, and we can now continue with the graph. Now, look at the graph. A graph is a straight line, and this graph passes through negative 1, 2. So we can say that a limit exists at function x as x is approaching negative 1. And the limit is 2 as x approaching negative 1, either from the left or from the right. So, rational functions can have point discontinuities as well as a vertical asymptotes. If rational expressions can be simplified, the function is still not defined as at this value of x, but the discontinuity becomes a point rather than a vertical line. Okay, I hope this example is clear here. Limit of fx is equal to 1 as x approaches 3. Sketch any function that approaches 3, negative 1 from both directions. Simplest example is a straight line. A function of x is equal to negative x plus 2. 3 cases. So this one is an example of a graph that passes through a point 3, negative 1. Okay? So try to observe in these 3 graphs. The f at 3 is equal to negative 1. Okay, like in this example. So if x is 3, so we come up with f of x negative 1. So f at 3 in this function is negative 1. How about this? The f of 3, if not equal to 1, oh no, is not, if not equal to negative 1, so that will be 3, 3. Now, f of 3 is undefined here. Okay? So, f of 3 is undefined. Again, limits do not exist when the function x approaches a different number from the right side of C than it approaches from the left side. Number 2, f of x increases or decreases without bound as x approaches C. Like our example earlier, that there is no limit as the values of fx grows larger and larger and larger. Okay? F of x oscillates between 2 fixed values as x approaches C. So we will consider these cases graphically. Now, like for this example, absolute value of x over x. So when x is equal to 0, the denominator is 0. So when x is 0, the value, if when x is greater than 0, absolute value of x over x is equal to 1. So we have the graph, a horizontal graph. Okay? So approaching 0 from the right, limit of fx is equal to 1 as x approaches 0. Okay? As x approaches 0. So, as x approaches 0, from the right, we have 1. This is called the right-hand limit. Now, look at this example. When x is less than 0, the value is negative 1 from the left. Approaching from the left, the limit of function of x is equal to negative 1 as x approaches 0 from the left. This is called the left-hand limit. When behavior differs from the right and left, in general, we can say in this function, limit does not exist. Again, if they do not meet at the same point, then limit does not exist. Function of x increases or decreases without bound as x approaches c. Like for this example, f of x is equal to 2 over x minus 3. Oh, look at the graph. This graph is undefined at 3 because if we are going to substitute x is equal to 3, then the denominator will be 0. It cannot be simplified. So there is a vertical asymptote at x is equal to 3. If you try to look at the graph, approaching 3 from the right, fx increases without limit or without bound. Approaching from the left, fx decreases without bound. When the function is increases or decreases without bound, then the limit does not exist. Now, this is the continuation of the rules or the theorem we have last time. For the following rules, we assume that limit function of x as x approaches a and limit g of x as x approaches a both exist. Like for this example, polynomial rule. If p of x defines a polynomial function, then a limit of p of x as x approaches a is equal to p of a, or the substitution law. Again, okay, finding a limit of a rational function. Example, we have x squared plus 2x minus 3 and x squared minus 3x plus 2. The solution will be rule number 7 cannot be applied directly since the denominator is 0 when we substitute 1 for x. So 1 squared minus 3 times 1 plus 1, so that will be 0, plus 2, that will be 0. Since the denominator will be 0, we cannot apply direct substitution. So we are going to factor this expression. So we have the factor of x squared plus 2x minus 3 is x plus 3 and x minus 1. Sa denominator is x squared minus 3x plus 2. We have x minus 2 and x minus 1. We have common x minus 1 and x minus 1. What is left is x plus 3 over x minus 2. Now this time we are going to substitute 1. And we come up with 1 plus 3 and 1 minus 2. 1 plus 3 is 4. 1 minus 2 is negative 1. So 4 over negative 1 is negative 4.